Hey, good afternoon, guys. Today we will code GPT model, GPT-2. So I didn't finish grading the some submissions for homework 3, but I noticed that some guys, I believe, who didn't take machine learning class, they didn't use optimizer step, and their training loop was just running the model without actually updating the weights. Um, but um, yeah. So today we will work with this notebook, and by tonight I will upload the homework, but you still have homework on BERT model. So this homework will be on prompt engineering with GPT model. So um, let's open this notebook. Oh, why it's not opening in Collab? Okay, I think I should change the link. Or we can open in Kaggle, it doesn't matter. I like maybe Collab more because it gives suggestions and for the code. Okay, so we will upload the weights of the pre-trained GPT-2 model, and because it was I believe in TensorFlow, we will convert into torch tensors. So this is just the code to upload the weights. And by default, I set up this runtime as CPU mode. But maybe when we will finish the coding, we will run in GPU or on GPU, because for inference, it will be slow on CPU. But for now, I don't, while we're coding, I don't use GPU time. Also, in that GPU model from 2019, there was additional triangular mask that we don't need to upload. So we skip uploading these weights. So we upload this state dictionary, the dictionary of weights. And you can see this is still small model. We can work with this on CPU. So the first, so let's remember which layers GPU does GPU model have. Do you remember what are the main layers in transformer model? So this is the transformer Do you remember what are the main layers? And GPU model is just decoder of the transformer. What are the main layers? What are the main components of transformers? Well, but this is encode decoder, but we need only decoder. So which layers we should actually write? Yeah, but what are these layers? So attention, and well, embedding is the input. Yeah, of course we need embedding. Well, normalization is just normalization. It's kind of yes. The second main layer is the feed-forward layer. So it's two linear layers, and yeah. So these are the main building blocks. Multi-head attention. After that, what? After that, we use residual connection. So after attention, the embedding will kind of look at the context, and they will go to feed-forward layer. After feed-forward layer, we again add residual connection from attention, and this is one transformer layer. After that, we apply another transformer layer. So in the second transformer layer, the embeddings now will be the outputs from the first transformer layer. So the outputs from the first transformer layer were context aware, and the outputs from the second transformer layer, they will kind of context aware, but on the level of the outputs from the first transformer layer. So we kind of force the model to continue thinking about to process the data. Then we add one more transformer layer, and in GPT-2, there are 12 transformer layers. So we will implement one, and then we'll just repeat them 12 times. Okay, and also the positional encodings. Do you remember why do we need positional encodings? And why people don't use this in computer vision?
To maintain where the words are within the sentence.
Yes, the temporal component. And in CV, they don't use these embeddings because the image is two-dimensional, and they just take pages of this image and take the attention. So there's no kind of real time dependency in images. So, okay. Okay, so let's start with the easiest layer, which is feed-forward layer. And the structure is, do you remember the structure of this FFN layer? Two linear layers with activation between. And the first layer kind of increases the dimension, and the second layer decreases back the kind of this shape. This is the activation function GLU that you didn't maybe see before. It's Gaussian E stands for Gaussian. I don't remember. GLU. Gaussian error linear unit. So it looks like CLU with a bump to make our RLU more smooth. So you remember RLU is not differentiable at the origin. So GLU kind of smooths this corner, and there is the expression for this function, but because it uses table functions in the GPT-2 model, engineers used approximation, and approximation is given by this expression. So it's not the GLU exactly, but it's approximation of GLU that works faster. And yeah, let's write the FFN layer using these building blocks to linear layers and one activation. So could you just dictate the code? And you don't need to raise hands. So you should pass. What should I type? So we can do in one line. We can do
Multiple lines.
how. So we can do in one line.
So x equals self dot fc x.
So the first connected layer. Yep.
Self dot j.
Yes. And we can do this in one line. Maybe it's so we start with self fully connected, self fully connected of X. Then we apply GLU activation. And then we apply the second fully connected layer. It's called projection. The names are taken from GPU model to use our dictionary to make easier to map these names to the dictionary with saved weights. So load projection. And there is a test with parameters from this GPT model. So if you pass this test, it means that you implemented this layer correctly. So this was fully connected layer. Now let's look at this masked attention. So in masked attention, first we apply a linear layer from embedding dimension to 3 times embedding dimension. Do you remember why do we need this linear layer? So this is how self-attention looks like. So we want to create 3 embeddings, and you can create 3 separate linear layers, or you can use one linear layer, but with size 3 times larger. What do you think? Is there any reason to use one linear layer with larger size instead of using 3 linear layers? Yes, because then you will need to perform 3 matrix multiplication operations, but it's not really important. It's very fast, but still for efficiency. So, and then we split this output into 3 chunks to get 3 embeddings, like yellow, red, and green, and blue, or query, key, and value. Value was red. So after that, yes, so we apply this layer and split into three parts. So we will get queries, keys, and values. Then you remember the heads. The heads were the parts of this embedding. So also we should split these embeddings into number of heads. So here we create a for loop over the number of heads, and every head will be selected by indices from, for example, 0 to the head size, then from the head size to the 2 head size, and so on. And you can do this with the syntax where you use a generator range. Is it generator range, or it's iterator? I believe it's iterator, where you use iterator to get the desired indices. Yeah, so we create this iterator, and this iterator will choose the indices for the current head. So we choose the current head from each embedding, from query, key, and value, and apply attention to these heads. And we will use built-in function dot product attention from torch. And this attention will be applied to the current head of queries, the current head of keys, and the current head of values. Okay. Then the rest of the code is written for you. Then we concatenate the outputs from these heads and apply linear layer to these concatenated heads. So this will be the output from attention, multi-head attention layer. And it's masked because we use parameter causal true. So it will be masked uh, by with this parameter. Let's see. Oh, the comma is missing. And we have some control sum to if we pass this assertion. Great. Now we implemented two main building blocks, the feed-forward network and attention layer. Now we want to build the transformer layer. And transformer layer, as you remember, is the in the original paper, it was attention and linear norm after attention. But in the current language models, typically linear normalization layer is used before attention and before feed forward. So in terms of performance, there is no significant difference. But as people notice, it's more stable for training. Because you remember, in attention, in the original paper, there was attention and then the normalization. Attention, normalization. So, but in large language models, current people use attention normalization before attention and before feed forward. Okay, so let's implement this transformer layer. I believe it's now straightforward. So when we have attention and when we have implemented FFN layer to implement this residual connection. So first we will apply normalization to attention and add our input. So this is the first part. Then the output from this first part, we should apply, we should pass to fully connected layer and add the residual connection. Okay, it actually proposes the correct code. X plus normalization. Oh, wait a second. We should switch these because first we apply normalization, then attention. Sorry. So in this case, And here it will be, yeah, now it's correct. First normalization and then fully connected and return X. So this is the transformer layer. And finally, we can initialize these layers with pre-trained weights from GPT model. In this GPT-2 model, this embedding dimension was 768 and number of heads 12. So we will just initialize our transformer layer with these parameters and upload the weights from our dictionary. So this was one layer. And now, as you remember, there were 12 transformer layers. So finally, let's look at GPT-2 model. So the input parameters, vocabulary size, number of heads, number of layers, also the maximum number of positional encodings, because as you remember, in the original model, in BERT model, the input size was 512. Now it can process hundreds of thousands of tokens. But of course, it takes time. So we have the weights for embeddings. We have the weights for positional embeddings. And finally, we have the output layer. Let's see, is layer norm. So somewhere we should have the output to the size of shape of the dictionary. Because as you remember, GPT model predicts next token. So in the output, we should get the softmax layer with probabilities. So, and it should have the size of the dictionary. So this layer norm goes after transformer layers, but before logits. Then this self H is the for loop over transformer layers. So why don't we see the output linear layer that actually has the output dimension of the size of the dictionary? So in this GPT-2 model, they use the trick that I mentioned briefly when we talked about general language models with logits, to that if you want to save the memory to use less parameters, then you can use the metrics with embeddings at the output. So in GPT-2 model, they used this trick. So that's why they don't have the output linear layer to the size of the dictionary, because they will use these metrics with token embeddings at the output. So yeah, so we create word token embeddings, positional embeddings, then sum up the embedding, then we pass this through transformer layers. And finally, we apply the linear layer. And in the end, as you can see, to get the output shape of the size of the dictionary, they just multiply it by the matrix of the embeddings. Because the matrix of the embeddings has one shape, the number of tokens, another shape is the size of embedding. So if you want to get the output shape of the size of the dictionary of the tokens, you can use this matrix. And yeah, let's initialize this model. Vocabulary size for GPT model is 50,000. And let's ask to predict the next most probable token for input phrase a quick. Maybe I can switch here to GPU. Well, at least I hope. Oh, I don't want to run the last. Okay, so yeah, at least I hope you understand now better the model itself. And then we use the most probable token with argmax here from logits. Yeah, it takes some time to upload the dictionary of the weights on GPU. Okay, so the most probable word, look, for the phrase a quick, according to GPT-2, which sounds reasonable. Now we can generate a longer phrase, and here is example with this starting prompt, the Fermi paradox, and we will use greedy approach to generate most probable token every time. And here's the output. The Fermi paradox. What is that? X very clever. Nick was not able to improve any of his specs. So it just generates something, but it's it doesn't make much sense. So to get better generation, we can decrease the temperature. Remember, if we use temperature parameter, then our distribution will be more flat. So we can divide our logits by temperature, for example, 0.9, and generate the text again. Well, now it looks a little bit better. The Fermi paradox is an uncoverable mystery in the math world. Well, it's actually in astronomy, but okay. um, yeah, so this is how you can generate text with GPT model. Just written by yourself. Also, you can, for example, use a prompt import pandas or import NumPy, and maybe it will continue to write the code, or maybe you can use the starter code def self-attention, and it will write the code for itself. So if you want to use larger models, for example, we can upload with the weights the dictionary for a larger model. For example, GPT-2 large. And initialize our model. Just we should change some parameters because it will have larger embeddings, larger, more transformer layers. Repeat C2 large. Config. So here you can find the parameters. Now, it's interesting. Beginning of sentence is the same as the end of sentence token. So the embedding shape will be 1220. The number of heads will be 220 instead of 12. And the number of layers, sorry. Oh, okay. Yeah, it was 12 and the number of heads and the number of layers. And the number of layers is 36 instead of 12. So we can use these parameters in our code. When we initialize the model here, 1280, number of heads 20, and number of layers 636. And it will upload the weights for this model with these parameters. And let's generate text with this model. The Fermi paradox has a very disturbing effect. Well, it's true on the idea of probability, which can be explained in terms of this whole science of information. Okay. Well, also, but you can see that the generation goes slower because the model is larger now. Yep.
What did you put in for the from pre-trained above?
So uh, so first I changed the imports in all the weights,
Okay, I
like
think I might have missed that.
like the first
Oh, that's
here.
what okay, thank you.
Yes, because maybe if you didn't change, it will try to use the dictionary from GPT-2, not GPT-2 large. Okay, so finally, So suppose we were able some. Okay, so finally you can do this just with a built-in um, Hugging Face repository, and then you just call it like this: transformers auto tokenizer GPT-2 or GPT-2 large, model upload auto model from pre-trained, and then you can generate text. Next time we will talk about this syntaxes. It's changed a little bit now. So instead of indicating these parameters in the method generate, we will use generate dictionary and pass generate dictionary um, with different sampling methods like nuclear sampling or temperature. Okay, so it should work. So it uploads now the weights from Hugging Face. The Fermi paradox is more likely to arise from environmental problems. Well, some terms are look reasonable, but um, well, it's just language model. Okay, so we can stop here for today, and we will have more fun with large language models, with GPT models, with family of GPT models. Actually, we will use. Oh, by the way, um, if you want to use the Llama model, then maybe it's a good idea to register on Hugging Face before, like, of course, we will use free language models, but uh, Llama model requires obtaining the license. So you can go to Hugging Face, and for example, if we want to use so this is free version. If we want to use let's say Llama 3, um, Llama 3, and for example 8, you don't want to use 70 billion parameters. 8, it should be 8 billion, I believe. Well, anyways, so you should look for any Llama model, and then you should click on the license somewhere. And you should write the request for license, and then you can use the token from Hugging Face to run officially Llama. Of course, there are some repositories that obtain the license and then just published these weights, but it's kind of a violation of their rules. But we will use also this pirate version of Llama from Hugging Face. But if you want to use the official version, you should obtain the license. Okay, we can stop here.